Hi, welcome to the video solution for Edexcel Physics past paper. This is Edexcel IAL Physics Unit 2. This is the third video of this unit, WPH12. So let's start. Question number 17. A teacher set up a signal generator connected to a two loudspeaker as shown. This apparatus was used to determine the speed of sound in air in an open space. A measuring tape was positioned along the ground at XY, which was perpendicular distance of 3 meters from the two loudspeakers. Okay, this is the arrangement. Two loudspeaker from signal generators, 5 meter distance between the speaker, 3 meter away. This is the line XY. The signal generator was set to a frequency of 160 Hz. This is frequency F. The students walked along the line XY. As they walked, they heard a series of loud and quiet sounds. At O, the students heard a loud sound. Explain why students heard a loud sound at A. This is the question about interference of wave, whether it is a light or sound or water. But remember, these types of question, whenever you have two different sources of wave, whether light or sound or maybe water or any type of two waves. So do two different sources of waves, and at some distance you will be asking about high or low, bright and dark. In this case they are saying series of quiet sound and a loud sound. So it's all about interference. So what happened, wave comes from one speaker like this and the other speaker from this, something like this, and they meet there. These two waves are interfering at that point, and also some waves are coming something like this and something like this, and they are interfering here. Some waves are from here and there, they are interfering at that point. So as you walk along the line XY, at some position or at some point you hear a loud sound, and at some point you hear quiet sound, and it's all about types of interference. So generally we say, if you can say, or you can see from the diagram, there is always some path difference between the two waves reaching at a point, like the red ones. So the wave 1 is traveling less than wave 2, so you have a path difference. And if you say the path difference is n lambda, if path difference is equal to n lambda, then you always have constructive interference. I'm writing in short, constructive interference that cause a loud sound in this case. And if path difference is n plus of half lambda, n plus half of wavelength, then it is a condition for destructive interference, and we hear nothing. The student is going to hear nothing, or the destructive interference, a quiet place. So that's the reason when students walk along the line, at some position they hear a loud sound, at some they hear nothing. But if you see at point O, now what is happening at point O? From loudspeaker 1, sound is coming at point O, and from loudspeaker 2, sound is also reaching at point O, and this O is exactly at the center from the two loudspeaker. So the distance traveled by the wave 1 from the loudspeaker 1 and distance traveled by the speaker 2, the wave 2, they are traveling equal distance, or they are covering equal distance. So there is no path difference. That means path difference between the two waves at O is 0. So if path difference is 0, or you can say 0 multiple of wavelength, or 0 lambda, or 0 simply, that this is condition always we have, constructive interference. We always hear a loud sound at the center of the position, or at the center of the screen, if this in case of light. So you will say that the sound waves coming from both speaker, they are traveling equal distance, and that means path difference 0. That's why you always hear a loud sound at O. That's the answer for part A. So, and you can write something like this. Part B. As the students moved from O towards Y, the sound becomes quieter until a minimum was reached. One student is still at the minimum point, while another student recorded from the measuring tape. The distance from O at which this occurred, he recorded this as 84 centimeter. Determine the speed of sound in air. So we need to look at the diagram for this condition. So this is the diagram, and if you see what is happening, a student is walking from O and towards Y, going up in this diagram. At some position like this, the students hear nothing. Position for the quiet sound, you can say, if you wish. So this is the position for the quiet sound, or nothing. And this is measured as 84 centimeter, but I'm not writing 84 because the rest of the distances are given in meter. So I said this is 0.84 meter, and we need to figure out from these informations, from the diagram, we need to figure out a speed of the sound in air. And if you see, how do we figure out speed of the sound? Generally, we say that speed of the sound V is equal to F lambda, and F is given in previous part, which is 160 Hertz. So this is fine. The only thing we need to figure out wavelength. So if we can somehow, if we can figure out wavelength, so we can find the velocity of the sound, or speed of sound. And how do we do that? How do we figure out this lambda? Remember, this is the condition for destructive interference, and for destructive interference, path difference is equal to n plus half of the lambda, as I explained earlier. And this is the, from the center, this is the first position of the quiet sound, or destructive interference. So for that first position, or the order of this position, n will be equal to 0. So path difference is equal to n is 0, so half of the lambda. Clearly, if we can figure out the path difference between the two sounds reaching at this position, so we can find the wavelength. That's what we need to do. Now, if you see the diagram, what is happening? If you see, so we can, like, sound is coming, reaching there, from speaker 2, it is there, and the distance between these two sound is this distance. The total distance, you know, it is 5. So from the center, this is 2.5, and this is 2.5 meter. 2.5 and 2.5 meter. So now we need to find the distance traveled by the wave 1 coming from speaker 1, like this, going there, and the distance traveled by the wave 2, or sound 2, from speaker 2. And if we can figure out that that distance and the distance for 1, so we can subtract these to figure out the path difference. And how do we do that? So if you complete the diagram, like, see here, and here. So now you can see this is 3, this is also 3. This distance we can figure out subtracting 0.84 from 2.5, and this distance would be equal to 2.5 minus 0.84, which is equal to 1.66 meter, and that distance is 2.5 plus 0.84 from here, so that distance will be equal to 3.34 meter. Clearly we have if you see this as the right angle triangle, we have a perpendicular and adjacent side. We can figure out this hypotenuse using Pythagoras theorem. Similarly for that triangle, so I'm calling the distance of the wave 1, or from loudspeaker 1, this distance is d1 and this distance is d2. So d1 would be equal to 1.66 square plus 3 square root. So d1 is equal to 3.428, or you can say 3.43 meter. Similarly, you can say d2 would be equal to 3.34 square, which is this, plus 3 square root, and final answer you would have here is 4.489 meter. You can round this off, d2 as 4.49 meter. So the path difference is d2 minus d1, which is equal to 1.06 meter. So now 1.06 is equal to half of the wavelength as per this condition, if you see here. So lambda is 2.12 meter. Now you have a wavelength, so V is equal to, as per this formula, V equal to F lambda, so 160 times wavelength 2.12, which is V is equal to 339.2 meter second inverse. This is the velocity of sound. Part 2, the teacher suggested using a microphone connected to an oscilloscope to determine where the loud sound and the quiet zones were located along the line XY. She said that this method would result in much less uncertainty than when students walked along the line XY. Explain one reason why this is a suitable suggestion. Clearly, if you see a person noting down the position for a loud and the quiet position or quiet region of the sound, for a person it will be difficult to judge exact position, but microphone will detect exact position because it is connected with the oscilloscope. So looking at the amplitude, we can figure out exact position of a loud and quiet sound or zone. So that's how you can compare, and you can say because of the microphone can detect exact position, so there will be less uncertainty if we use microphone. A student suggested that equally valid result would be obtained if the experiment was performed in the classroom. Criticize the suggestion. No, the student suggested a wrong condition. It is because in a classroom we have walls and we have roofs, so it is possible that the sound waves reflect from the walls and the roof and reaches at the point of observation. That means if you are doing like this is the source of sound and open space, so only the sound can reach from the source, only two waves can reach. But if you are using in a room, so you can say some waves might reach after reflecting, like this, something like this. So you can imagine at the point of observation there are more than waves are reaching at the point of observation, so the interference will not be prominent, or it will be less pronounced, or it will not be observable, that can be studied if more than two waves are reaching. So that's how you can write this reason. Question number 18. An endoscope is a medical device that can be used to see inside the digestive system. The endoscope contains a bundle of very fine fiber glass or glass fibers. Light is directed into the fibers to eliminate the part of the digestive system being investigated. Okay, it's all about total internal reflection. Light travels along the glass fibers by total internal reflection. So this is a fiber wire, glass, and so on. State the condition required for total internal reflection to occur. Remember a typical question regarding total internal reflection, the necessary condition. So there are two necessary conditions. The light should enter from dense medium to the rare medium, or it must reaches at the boundary of a rare medium. The condition number one, meaning the light must traveling from dense or high refractive index and reaching the point where the boundary of a less refractive index or rare medium is there. And the second condition is the incident angle should be greater than the critical angle in order to the light be a total internal reflected. So that's how you say that. Number one is light must transmit from high refractive index to the lower one, and the incident angle must be greater than the critical angle. A ray of light is incident on the end of a glass fiber and refracts as it enters the glass. Explain why the light refracts as it enters the glass. Clearly, glass is a denser medium, and due to high density or high refractive index, speed of the wave or speed of the light decreases. And due to decrease in the speed of light, direction of the light or the wave changes. That's why we say that we have a refraction. So 2 points: decrease in speed and change in direction. That's what we call refraction. C. The diagram shows a ray of light being totally internally reflected at one side of a glass fiber and then refracting as it leaves the end of the fiber. The angles of incidence at the boundary between the glass fiber and air is equal to the critical angle. C for glass air interference, the ray enters water, it leaves glass the fiber. So it is entering, this is critical angle as per the condition, totally internally reflecting and emerging out into the water. Determine the angle theta of the emerging ray and the normal. So we need to figure out this theta, and in the diagram we are given three refractive indexes. So for water is 1.3, for glass 1.5, and for air is 1. So first we need to figure out this critical angle because this is C, and if we need to find this, if we can figure out the C, that means we can have the other angle because of total internal reflection. So incident angle equal to reflected angle. So let's just work out with the C, and this is critical angle. So sine C, critical angle of sine of critical angle is 1 upon n, and n is the refractive index of the medium from which light is coming. So sine C is equal to 1 divided by 1.5, and then C would be equal to 41.8 degree. So this is the critical angle here. That means this angle is also 41.8. Clearly, if you see, if this angle is 41.8, then this angle is also 41.8, the alternate angle. If you see the geometry, two parallel lines, this line and this dotted line, these are parallel, and this is the transversal line. So 41.8 and 41.8, meaning we have this angle which is the incident angle for the other boundary, and this angle is 90 minus 41.8. So incident angle for water I is equal, this is I. If you wish, you can mark these symbols, similar symbol you can use, or some other symbol your own. So I and I would be equal to 90 minus 41.8 or 81. So I is equal to 48.2 degree. This is 48.2. Now we have a simple refraction. So we can use approach of n1 sine theta 1 is equal to n2 sine theta 2. This is a general approach of refraction. N1, this one is showing the angle and the refractive index of the medium 1, and this is for medium 2. Now we can say that this is our medium 1 and this is our medium 2. So I can apply N1 is the refractive index of the medium 1, which is 1.5, and sine theta 1 is the incident angle. So sine of 48.2 is equal to N2 is the refractive index of the medium 2, which is 1.3. So 1.3 sine of theta 2, angle in the second medium, which is theta, need to find. So theta. So sine theta would be equal to 1.5 sine of 48.2 divided by 1.3, and then theta would be equal to, if you figure out this, then 59.3 degree. Question 19, a student carried out an experiment to determine the EMF E and internal resistance R of a potato cell. The potatoes used in experiment was connected to a rest of the circuit using electrode of the two different metals as shown. Okay, this potato, two electrodes. Complete the diagram below to show the circuit that could be used in order to determine E and R for the potato cell. A typical question about internal resistance and the EMF. This is the potato cell and we have internal resistance inside. So we need to complete the circuit. So you can complete the circuit like you can connect an ampere meter in series like this, and then you can connect you know, a variable resistor in series. And then because we need to study the potato cell, so we'll have to connect a voltmeter across the potato cell. So this is a circuit diagram we can use to find E and R of the potato cell. Part B, the student completed the experiment and plotted a graph showing the relationship between potential difference V and current I as shown. Okay, so this is voltage, this is current in milliampere. Use the graph to determine the value of epsilon and R. Idea about these types of question is, if we need to find internal resistance and EMF, remember, so we have a graph of V against I, and we always have a line with negative gradient. So the gradient of this line is basically minus of R, negative of the internal resistance. And if you extend the line and you intersect this line at the voltage axis, this y-intercept gives you the EMF E. That's what we are going to do for this question. So we are going to plot a line of best fit, and we find the gradient of that line and the y-intercepts. So here's the idea, and that's what we need to do. This is the line of best fit. Now I am going to choose 2 points on the line. So it's up to you. You can choose any 2 points as large, a triangle of 2 points as big as you can. So I am choosing, let's suppose the best point for me is 0.45, I guess. Yeah, this is the point. And the coordinate of this point will be 0.45 comma 0.1. Remember, I have a milli here, so 10 to the power minus 3. Don't forget in your final calculations, it's not just 0.45, this is 0.45 into 10 to the power minus 3, which is milli. And the next point I'm going to choose at I guess, let's just take this point here, and the coordinate of this point will be 0.08 into 10 to the power minus 3 comma 0.25. Now let's find the gradient. If you find the gradient, then gradient would be equal to y2 minus y1. So 0.1, this is 0.25, I guess. Yeah, 0.25 here. So gradient will be equal to 0.1 minus 0.25 divided by x2 minus x1. So 0.45 minus 0.08 into 10 to the power minus 3. Once you solve this, gradient would be equal to minus 405.4, and you know that my gradient is negative R. So negative R is equal to negative 405.4 ohm. Negative is cancelled, so resistance, internal resistance is 405.4 ohm. That's the internal resistance. Now what about the E? The EMF is the y-intercept. So you just extend the line something like this. So you can say it's 0.28 or 0.285, something like this. So you can say from here, you mentioned this is 0.285 volt or 0.29 if you wish, or 0.28, 0.29 volt. This is your EMF E. C. In a separate experiment, two resistors with equal resistance R are connected to a battery with internal resistance R, and with the two resistors firstly in a series arrangement, diagram A. This is a series arrangement with the two resistors firstly in series arrangement, diagram A, and then parallel arrangement in diagram B. Okay, this is parallel arrangement, same power supply, same internal resistance, same EMF. Explain which if either of the two arrangement would lead to greater value of for the terminal potential difference. Clearly, if you see, we have a two different circuit. One is in one circuit we have a resistances in series, and the other one resistances in parallel. So the idea is, in series circuit, the total resistance R is sum of the resistance. So total resistance is sum of the individuals. So R1 plus R2. Clearly RT will be greater than all of the individual resistances, whatever, it doesn't matter how many are. So the total resistance is always higher than the used in the circuit. And in parallel circuit, total resistance we find is 1 upon RT is equal to 1 upon R1 plus 1 upon R2, etc. That means these are the reciprocals. So the total resistance for parallel combination always decreases, or lower or less, whatever word you use. So if resistance is low, then amount of current will be high. If resistance is higher, then amount of current will be less. So these are the two key points, just you keep in your mind. And then if you see, if resistance is higher, amount of current is lower. So higher the resistance, then voltage drop or V will be higher. Now if you see the whole situation, what is going on? So V is equal to E minus IR. If you see, this is the equation for EMF and the terminal potential difference. So now for series circuit, what is happening? Series circuit, total resistance is increasing and current is decreasing. If current is decreased, so if you see this term IR, this IR is the lost volt. So basically, if you see, mainly V is depending on three factors here: E, I, and R. E is the EMF. So for the both of the circuit, E is same. There's no changing of E is the EMF. So E stays the same. So V does not, for E will be same. So we cannot discuss this. R is the internal resistance of the power supply. This is also same. The only thing is changing between these two circuits is the amount of current. So for series circuit, amount of current is decreasing. So the product IR will be decreasing. So IR is the lost volt will be decreasing. So for series circuit, IR is less than the parallel circuit. That's why V will be higher. So that's how you can combine all these points in your statement for explanation of this question. So I'm summarizing again in just 2 or 3 words. So in series circuit, the total resistance is greater. That's why amount of current is less, due to which the lost volt is decreased and E and R stays same for both of the circuit. That's why V is higher for the diagram A. This equation is not V is equal to E plus IR. This says V equal E minus IR. So this is the wrong one. I'm sorry about that. So clearly you said that IR is less, is decreasing, so the difference will be increasing. That's why V is greater. Thank you very much for this video and have a nice time.